we're now finally ready to prove the existence of a left Harmonic measure. So from last class, we saw that we constructed an outer measure from our candidate of the left Harmonic measure. And just recall the following fact from measure theory. So suppose we have an outer measure, then we can always look at those what we call the basically Carathéodory measurable sets, basically all those A where if you evaluate any outer measure on E, then you can break it into E intersect A and E intersect A complements. Turns out all these measurable sets, in the sense of Carathéodory, is actually a sigma algebra. And moreover, if you restrict your outer measure to the sigma algebra, then you actually get a measure. Okay, so that's how we actually construct the Lebesgue measure. You do the Lebesgue outer measure and so on. Okay, so from last class we saw we have an outer measure. Okay, so now let's try to prove that we can restrict to this measurable set and we get a Radon measure. And to show that, basically we need to show that all the Borel sigma algebra is a subset of all these measurable sets. So I basically need to show that this measurable set contains the Borel, and because it's sigma algebra, you just need to show that every open set is measurable. Okay, so essentially what we need to prove is the following. We need to prove for every U open, U is going to be measurable in this sense. Okay, so it's mu star measurable. By mu star measurable, I mean satisfy this equality. All right, so basically I need to show that for every E, then this equality holds. And again, without loss of generality, is some standard trick from measure theory. We may assume that the mu star of E is less than infinity. Okay, if it's infinity, there's nothing to show. And I just need to show, suffices to show one side of equality because the other side is basically the subadditivity. I just need to show the mu star of E is greater than or equal to the right-hand side. Okay, so because less than or equal to is just the subadditivity. All right, so that's what we need to show first. So from there, we actually construct a measure, okay? All right, so to show this inequality, we need to do some approximation, okay? So let's fix epsilon greater than 0. Then I can pick something that's, I need to approximate the left-hand side, which is mu star of E. So I can pick something that's approximated by open set, okay? So pick some V open, so that E is contained in V, and it's a good approximation. So mu star of E is going to be less than or equals to mu star of V, and less than or equal to some epsilon within some epsilon range. So let's say mu star of E plus epsilon over 3, okay? And now we need to do approximation of E intersect U and E intersect U complement, okay? So if I consider V intersect U, okay, so U is my, I should, instead of A here, I should set U here. So here I want to show U is measurable, so U is here. So V is a nice approximation of E, okay, so let's consider U intersect V. Well, because your space is locally compact, there exists a K compact, and that's like inside there, and it will approximate the measure of V intersect U nicely. So I have K, so that the mu of K is going to be less than or equals to mu of U intersect V, but less than or equals to mu K plus some epsilon over 3, let's say, okay? And if you look at what's the next one, well, you want to do the E intersect U complement, okay, but that's not an open set, okay? You cannot say there exists a compact set that approximates the mu star of that nicely. Well, so what do you do? Well, you do the other thing. You have a compact set K here, so its complement is open, and its complement is kind of approximating this U complement, okay? Well, it's kind of approximating the part that's not inside U and but inside E, okay? So that's kind of the idea. So there exists a L contained in this open set, which is V intersect K complement, so that you have a nice approximation. So mu of L is less than or equals to mu of V intersect K complement, less than or equals to mu of L plus epsilon over 3, okay? So that's the next approximation. So now we just need to show our approximation is good enough. Okay, so first of all, let me briefly talk about why this is a good approximation of this E intersect U complement. Okay, so because you clearly have the following, so K is a subset of U intersect V, so K is a subset of U. So your K complement contains U complement. So what you have is if you consider mu of V intersect U complement by the monotone, you know that this is going to be less than or equals to mu of V intersect K complement, but that's equals to your mu of L. Okay, so that's the mu of L, and sorry, mu of L plus epsilon over 3. Okay, so you use this inequality here. All right, so basically the mu of V intersect U complement is sandwiched between around here. Okay, it's bounded above by that. All right, so now let's put everything together. So let's do, we want to approximate E intersect U plus the mu of E intersect U complement. And first of all, let's do the following. So the first one is bounded above by mu of V intersect U. And the second one is bounded above by V intersect U complement. Standard trick, you replace E by the slightly bigger open set V. And for each one of them, we have an approximation. So we have one here, and we have another one here. Okay, so this is bounded above by these two inequalities. So the first one I bounded above by mu of K plus epsilon over 3. And the second one, I have a mu of L plus epsilon over 3. Okay, so I get these two. And now the good thing is that K and L, they are going to be disjoint. Okay, so from our construction, L is a subset of, is the complement of K. So the K and L are disjoint and they're compact. So we know from the additivity on these compact sets, we know that this is equals to mu of K union L, okay, and plus 2 epsilon over 3, okay. And what's the K union L? Well, is everything is contained in V here, so it's clearly less than or equals to mu of V plus 2 epsilon over 3. And the mu of V, again, you use the last approximation. You have mu star of E plus another epsilon over 3, so you get epsilon. Okay, so you finish the last bit of this proof. Okay, so basically that epsilon goes to 0. You get all of these open sets is mu star measurable. Because the mu star measurable set is a sigma algebra, so you get all the Borel sets are mu star measurable. Okay, so the conclusion is for every E, well, I shouldn't say E, I have an E over there. So for every A, let's say Borel, A is going to be mu star measurable. So basically, when you restrict it to the Borel set, you do get a measure. Okay, so the mu star restrict to the Borel sigma algebra on G is a measure. Okay, and again, let's forget about the star. Let's just abuse the notation again. Let's let it be the mu instead. Okay, so let's just ignore the star from now on. Okay, so now we finally constructed a measure. Okay, we started from a mu defined on the compact, we extended to the open set, and then to an outer measure, and then finally we restricted now to a Borel measure. Okay, it's finally a measure. And we only have one last thing to show is actually a left Haar measure. Okay, so here's the proposition. So I want to show that this mu we obtained finally is a left Haar measure. All right, so to show it's a left Haar measure, well, we already know it's a measure. So I need to, first of all, show it's actually non-zero. So why it's non-zero? That's trivial because we saw that, for example, if you can say the mu of U of K0, that's always going to be equal to 1, or you can say when K has non-empty interior, then its mu is always strictly greater than 0, but in any case, you will have this mu of this K0 is equals to 1. Okay, so now it's slightly clear how this K0 came into play. Okay, that's kind of the unit space you chose to be. For example, on the real line, you can choose the K0 to be the unit interval, and you deem it to be a measure one set, and then you do the other scaling. Okay, so that's where it came from. But anyways, you know that it's not equal to empty, but not equal to 0. Okay, so you get something that's non-zero. The regularity actually follows just from the construction, okay, because your mu on the open sets are the supremum from inside, and the mu of all the other sides are infimum from outside, so mu is clearly Radon. Okay, so clearly Radon. The mu on all the compact sets from our construction of this mu, we know is finite on the compact. Okay, so it's clearly regular from the definition, so it's Radon measure. And the last thing you need to know to show is basically it's going to be left invariance. And this is really goes back to our construction of this index, this k over some u. So if you have a compact set k, and if you say over some u, then because this is measured by how many things you can cover this k, then you can convince yourself if you translate this k by any g, that's still going to give you the same covering. Okay, if you have a cover of k, you translate it again by g, you get a cover of gk, and you translate by g inverse, you get a cover of k. Okay, so these are the same. So you also have mu u of k, that's going to be left invariant. Okay, so mu u of gk, and because that's left invariant, you do the same limit argument, the continuity on those big set x. Again, mu of k is equals to mu of gk. So mu is going to be left invariant on your compact set. And then you do all the infimum, supremum, and basically convince yourself that's going to be left invariant for all the Borel sets. Okay, so for every A Borel. Okay, that's going to be clear. Okay, so we finally proved that there exists a left Haar measure. Okay, so I just want to, now we need to prepare to show that this Haar measure is actually unique up to scalar multiplication. All right, so I want to do two little lemma. So let's do one little lemma. I want to show that if you have something for every non-empty set U, okay, that's open, then actually the Haar measure of your open set is always strictly greater than 0. Okay, it's never going to be 0 on the open sets. Okay, the proof is kind of simple. So because you have some, let's say k has a non-empty interior, so let's say mu of k is greater than 0. You can even just pick k0 here. Then you can consider how many open cover you need by translating this u. Okay, it's a finite number, so let's say it's equal to n. So basically, there exists a g1 up to gn in G, so that your k is contained in the union of this GIU. So because you have a measure, so on one hand, you have a mu of k strictly greater than 0. And by the monotonicity of your measure, that's less than equals to the mu of this union GIU, where I go from 1 to n. It's a finite union. Okay, by subadditivity, you know this bounded above by I going from 1 to n of your mu of GIU. But left invariance tells you each of these is equals to mu of u, so this is just n times mu of u. And so n times mu of u is strictly greater than 0, so mu of u is greater than 0. Okay, so that's clear. And because of that, well, the one immediate corollary is that once you have a measure, so measure is closely related to the integration. So suppose you have some f inside a compactly supported function on G continuous, and say it is positive, so it's never 0. So let's say f is non-zero. Then the integral of this f respect to your measure is going to be strictly greater than 0. Okay, your f is non-negative always, compact supportive, and as long as your function is not a 0 function, you get something that's the integral is always 0. And the proof is really simple. Okay, so your f has to be non-zero somewhere, so there's some x where your function is non-zero. And you just look at where this function is greater than, say, half of the sup norm, and is at least the integral is at least that, multiplied by the measure, and you know from the last lemma, you know the measure of this open set is not, strictly greater than 0. Okay, so just pick, say, u is all the x, where f of x is strictly greater than half of the subnorm of f. Okay, so that's going to be open, and your integral is greater than or equals to, well, the half of the subnorm times the measure of u, which is strictly greater than 0. Okay, so I leave the detail for you. All right, so I just want to point out one more thing about this Haar measure. So again, once you have a measure, you can talk about the integration. And one thing is that because of this left translation of the measure, you also have a left translation of the function. Okay, so suppose you let mu to be a left Haar measure, then what you have is that for every f inside the cc of g, then if you consider the integral of f d mu, okay, that's going to be the same as the integral of the left translation by some y. Okay, recall the left translation, evaluate at some point, you just do the evaluation at y inverse x. Okay, so that's equals to that. Or sometimes equivalently, you can write the following. So equivalently, another way of writing this is integral. If you want to integrate fx d of mu x, that's going to be equals to the integral of f of d mu x again, but you can multiply something on the right. Okay, y or y inverse doesn't really matter. Okay, so the proof is fairly simple. Okay, you do the simple functions and you approximate the compactly supported function by simple functions, and you should get this quite easily. Okay, but this is basically telling you how you can translate from the translation of a measure to the translation of the function.